Okay, so the first speaker is Yair Shokef, who will talk about combinatorial metamaterials.
Okay. It's really a pleasure to be here in Cambridge and in this symposium honoring Sir Sam Edwards. I'll start maybe with a very brief personal remark. So actually, so it's indeed a pleasure to be here in Cambridge and in this workshop and to honor Sir Sam Edwards. And actually the first research proposal that I wrote was a bit over 20 years ago. I wrote a small application in order to come for a summer here in Cambridge and to collaborate with Sir Sam, and indeed I eventually spent here about a month, I think, which was great. We talked a lot about granular matter, trying to understand what is compactivity and what can be done with that. I benefited a lot from those discussions. But today I'm going to tell you about completely different things that I'm working on in Tel Aviv. And obviously I'm not going to tell you only about my work, but about work of lots of people that I want to acknowledge now, because I probably won't have time at the end of the talk. Lots of people in my group during the last 2 years, and also great collaborations with lots of people from different places around the world. And this is the first talk about metamaterials. Today we'll have a few more different perspectives about metamaterials, and I'll try to give you a bit of my perspective of why should we study metamaterials and what interesting things do we have there, both from the or mainly from the basic science and theoretical physics point of view, but I'll hint also to some applications that out there people are working on things that have connections to industrial applications eventually. So I'll start with something which clearly is not a metamaterial. This is ice. And if you don't know, ice has residual entropy at 0 temperature. So the third law of thermodynamics tells us that at 0 temperature the entropy should vanish. In ice, it doesn't vanish. From heat capacity measurements, you can identify the entropy, integrate down to 0 temperature, or the lowest you can get, and there seems to be some excess entropy there. And Linus Pauling explained the source for this excess entropy quite some time ago from the concept of frustration. He didn't use the word frustration, but essentially it's because in this tetrahedral structure of ice, there's some 2 in, 2 out rule for how the protons arrange around every oxygen, and there's degeneracy there, and that degeneracy leads to entropy even when you minimize the energy, namely in the ground state of the system. Today, we and many others are looking on all kinds of artificial systems, and specifically what's referred to as artificial spin ice. And these are artificial structures that are fabricated. Here we're seeing a 2-dimensional square lattice made out of these elongated ferromagnetic islands on length scales of a few hundred nanometers, and you can now arrange the orientation of these macroscopic spins, if you want, in order to tailor the interaction between them. And once you go to slightly larger length scales, you can visualize, okay, here's an experimental image of what's the spin state of each individual meta-atom, if you want, in your system. You can also manipulate them. Again, certainly in these artificial spin ice systems, people know how to come with the magnetic tip and apply forces on individual magnets here. And certainly when you go up to slightly larger length scales of micrometers for colloidal systems, or millimeters or centimeters in mechanical systems, you can come in with optical tweezers or with your fingers and manipulate things at the single particle level. And we can use all of these artificial systems in order to study condensed matter phenomena, and also to achieve very precise control, and hopefully identifying and studying different phenomena in these systems could also lead to applications, because generally in life, once you understand something very well, you can also take advantage of it and use it in order for all kinds of things. And indeed, when you go to the centimeter scale, maybe one of the canonical examples for mechanical metamaterial is a perforated sheet of material. So the red you're seeing here is just the background, the table that this blue perforated sheet is placed on. So you have some elastic material which has holes in it, and the holes here in this case are arranged in this nice square lattice. Turns out that if you take such a perforated sheet and compress it in one direction, typically we know from elasticity that if you have some material and you compress it in one direction, due to the Poisson effect, it spreads out in the orthogonal directions. Turns out that if you now coarse grain and don't look at these holes, just consider this as some a macroscopic system, when you compress in one direction, this material shrinks in the opposite direction, which means that it has a negative Poisson ratio. Okay, so here's a very simple demonstration of a weird and unusual phenomena that, okay, maybe someone could take advantage of this in order to build some mechanical system that could perform better if it has a negative Poisson ratio. Okay, but now I want to look at this from this point of view of analogies to condensed matter physics. So I want now to look at the details of what's going on inside the system and not just look at this coarse-grained macroscopic behavior in which we have this negative Poisson ratio, which again generated lots of excitement. And I want to look at the displacement field. Okay, so I'm reminding you that red is just the background, blue is the material, and now I just want to draw an arrow that designates the motion of each material point from my initial reference relaxed configuration to this deformed configuration. Okay, and these arrows look like this. Okay, and this texture is exactly the ground state of our square lattice artificial spin ice. Okay, where these arrows are not displacement, but rather magnetization. Okay, but mathematically, again, coming just from a basic statistical mechanics point of view, these arrows are exactly the same. The state of the system is exactly the same in this mechanical system and in this magnetic system. Okay, so now what we will do, and at least what I do within this context of metamaterials, and when I say metamaterials, I'm referring both to mechanical systems like this and to all kinds of artificial systems like the magnetic system that I showed you before, and also colloidal systems, which I won't get into today. What I'm doing is trying to take advantage of the fact that many of these systems naturally tend to have discrete behavior, discrete or almost discrete degrees of freedom. Okay, so even though this elastic system is continuous, the deformations are continuous, still the motion of each point here is either up or down, and you have more or less the same displacement magnitude for all the horizontal points, and more or less the same horizontal displacement for all the vertical points. So you can describe the deformation here using a spin model, which is something, again, coming from statistical mechanics, is something very useful when you have a system with some discrete behavior, and then we're going to use all kinds of things that we're used to from condensed matter physics or statistical mechanics in order to study these systems. And I'll try to show you that we have all kinds of phenomena here related to frustration that I already mentioned before, defects, topology, and I'll give you some a presentation of something that at least I'm doing in this context. And from this theoretical understanding of these different condensed matter phenomena in such artificial systems, we're able to obtain desired responses for these artificial structures, and hopefully down the road this could be useful also for applications that I'm not going to talk about today, but there are people that are very much interested and actively working on trying to use metamaterials, specifically mechanical metamaterials, for all kinds of applications. Specifically, what I've been obsessed about for the last 2 years is combinatorial mechanical metamaterials, and I'll try to explain what I mean by that using this example. So just consider the triangular lattice, and now each triangle in this triangular lattice is going to be made out of these 8 sticks, okay, that are connected at perfect hinges. Okay, why do I want to use this structure? Because this structure, you may already recognize that this structure has a zero energy mode or floppy mode of deformation. Okay, so I can take this triangle and I can deform it either in this direction or in that direction without changing the length of any of these bars. Okay, so assuming there's no resistance at the hinges, this costs zero energy, and therefore this thing is floppy. It will just deform spontaneously, easily, right, without applying any force or with a negligible force. But now, where does the combinatorics come into place? I'm going to use the fact that this structure is anisotropic. Namely, here it's oriented in one way, but when I repeat it in the lattice, okay, besides this issue that I have up-pointing and down-pointing triangles, even in all the up-pointing triangles, I have 3 possible orientations in which this building block can appear. So I can now build a generally non-periodic structure. Okay, so even though this is lattice-based, I have a triangular lattice. Each time I repeat this block in the lattice, I can decide what would be its orientation. Okay, and I have 3 possible orientations, which I've colored here in red, blue, and green, and I can get this complex structure. It's complex, however, this complexity is discrete. Okay, so again, I'm very excited about that because then we can use all kinds of things that we're used to and we know how to do in statistical mechanics. So it's discrete in the structure. Okay, so I have some discrete variable that tells me what the orientation of each triangle in this lattice. Okay, so one question I can ask is if each one of these building blocks is floppy, again, if it was isolated and disconnected from the rest of the lattice, namely locally there's some floppiness, when I now combine them together, is this macroscopic system also floppy, again, at some global scale. So in order to understand that, I'm going to analyze the minimal place in the system in which there could be a conflict between the tendency of these individual triangles to deform. And that, namely, I'm going to try and complete some path or closed loop in the lattice, starts from some block, asks, okay, if this block behaves in a certain way, how should the block next to it deform, how should the one next to that deform, etc., until I return to the one I started from, and then I'll test whether I can consistently deform all of them simultaneously. The shortest path I can think of in the triangular lattice is just 6 triangles around the vertex in the lattice, and these are just 2 representative loops, and I'll try to see whether I can now deform these small structures. And it turns out that I can easily deform the one on the left. However, if I'll try to deform the one on the right, I'll get a contradiction here, namely this structure is frustrated and therefore it would be mechanically rigid, while the one on the left would be mechanically floppy. Okay, and you can also see this experimentally here in the bottom, where instead of having perfect rigid bars and perfect hinges connecting them, this is some soft 3D printed elastic material that is just thinner at the edges, so it's easier to deform it at the edges, where these bars are thicker and it's hard to deform them. And even without performing this experiment, just by viewing these videos I just showed you, you can see that here on the left, all of these yellow bars stay straight, whereas here on the right, you can see that many of them are bent, which means that some of the deformation here on the right had to change the end-to-end distance of some of these bars by bending them, and that is harder than just changing the angle at the fin connection at these hinges. Okay. So now the reason that this configuration on the left is floppy and the one here on the right is not, is that here on the left I have an even number of connectors, and here on the right I have an odd number of connectors. And again, this discreteness and mapping to spin models that I like is useful also here, because the basic floppy mode I showed you before had to do just with motion into the triangle or out of it. So I can define some binary spin variable, just plus or minus 1, just telling me whether I move in or out. And whenever I have a bar, that's like an anti-ferromagnetic interaction, because I want to flip that variable. And if around my loop I have an even number of spin flips, I can return to what I started from. If I have an odd number of spin flips, this means there's frustration. This is exactly like what we know from spin glasses. Okay, so this concept of frustration was termed in the context of spin glasses. Maybe if you have a disorder arrangement of these interactions, of say ferromagnetic and antiferromagnetic interactions, when you complete the loop, if you have an odd number of antiferromagnetic interactions, you will have frustration. But now we can ask ourselves, can we build a mechanical metamaterial, a big lattice like this, such that there would be no frustration, such that there would be some macroscopic floppy mode? And the way to do that is to, again, define these spin variables and say, okay, now I didn't decide what's the orientation of each block here. I'll first try to find the shape of that floppy mode, and once I find the shape of the floppy mode, from that I can infer what should be the arrangement of the triangle, such that that would be the shape of my floppy mode. And in order for a displacement field to be consistent with this, I need every triplet of spins to not be all in or all out, and that, you know, and in order to obtain that, I can require that I'm in the ground state of this Hamiltonian, which essentially just maps to being in the ground state of the antiferromagnetic Ising model on the Kagome lattice, and the ground state of that model has extensive degeneracy, namely the multiplicity, the number of possible configurations that satisfy that condition grows exponentially with system size. So I can now easily take one of these configurations that belong to the ground state of the Ising model on the Kagome lattice with antiferromagnetic interactions and build from it a deformation field, and from that deformation field to build a metamaterial which would be mechanically compatible. Okay, so this structure here, which looks pretty messy, is not random. It was generated from the ground state of the antiferromagnetic Ising model on the Kagome lattice, such that it would have a floppy mode, and you can indeed see this experimentally, that this structure looks messy, but actually it has a global floppy mode. Whereas if I would randomly orient all the triangles here, most likely there would be lots of frustrated loops, and it would be mechanically rigid. We can do the same thing in 3D. Okay, so it's easier to see things in 2D, but in principle we can extend everything also to 3D. Actually, that's where we started. Same concept, that you start with an anisotropic building block. You orient each block in the lattice in a different direction. You have a huge number of possible structures you can build that grows exponentially with the number of blocks. And many features of the dynamics are determined just by the discrete mutual orientations of the blocks. So in 2D, our minimal loop that we had to test whether it's frustrated or not was 6 triangles around the vertex in the lattice. In the 3-dimensional simple cubic lattice, the minimal loop would be 4 blocks around an edge in the lattice. So now each edge in the lattice is the basic object which would be frustrated or not. And there are certain mutual orientations of these 4 blocks, and here I'm just showing you a top view of that give you an even number of spin flips, and there are a few that give you an odd number of spin flips, and those that give you an odd number of spin flips are mechanically frustrated and will refer to such an edge as a defect in the lattice. So now, if we make sure we don't have any frustration in the system, similarly to what I showed you before, also in 3D, we can, for any deformation texture we want, we can design a metamaterial that would have a floppy mode that looks according to that. But you can use this not only in order to cause the metamaterial to deform according to a certain texture, but you can also give this metamaterial a response which is sensitive to this texture. Namely, you can take your metamaterial, press on it with different textures, and the compatibility between the texture that you're pressing and the texture that the material is designed for determines the mechanical rigidity of this metamaterial. Okay, so you can reach a pretty wide range of stiffness just by these combinatorial or discrete degrees of freedom of the texture that you're pressing on. Okay. However, I'm showing you here one side of this metamaterial. The deformations here alternate regardless of what orientation of each block, which means that the texture on one boundary of the system determines everything inside the metamaterial and also on the opposite side. So what you're seeing here is the less famous video of the backside of this smiley face, and hopefully you can see that what you're seeing here is an anti-smiley. Okay? Because as you move into the lattice, the deformations just alternate between every pair of opposite faces of each block. Therefore, here, when we have an even number of even system size of 10 by 10 by 10 blocks here, we will have the opposite texture on the backside. So now, this means that you can use this in order to design the deformation texture only on part of the boundary of this metamaterial. Actually, it turns out that using these blocks, you cannot even design 3 different faces. You can design more or less only just one face. But in order to design the entire boundary, what we had to do is to use blocks that break this holographic order. Namely, I now need to use blocks that do not have this alternating staggered displacement that we had in this simple block shown here. So we generalized to all the possible responses of a single block. Turns out that some of them indeed induce this holographic order, but some of them do not induce holographic order. And with these non-holographic blocks, the behavior in the bulk is not uniquely determined by the boundary, and we can design the texture on the entire boundary of this metamaterial. So again, if you want to have this, I know, 4 different pictures on these 4 faces of this metamaterial, we could identify what should be the orientation of each one of the blocks in the system in order to get this. We can do the same thing in 3D, in 2D. So again, this is the non-holographic block in the square lattice, and if you want to have a certain texture on its boundary, you can orient the blocks like that, and this is an actual experimental demonstration that we performed. So what I told you so far was in structures in which we intentionally made sure that there's no frustration in the system, there are no defects. But now we can see these defects in a controlled manner. So here you're seeing another metamaterial system, again here in the honeycomb lattice, with a single defect here. And this defect has a topological property that any loop going around it, so the minimal loop going around it, has an odd number of these effective anti-ferromagnetic interactions, but now also every big loop going around it far away, okay, it's something maybe similar to a Berger's vector, also has an odd number of these effective anti-ferromagnetic interactions. This means that if I now go from the left side of the boundary to the from the left side of the system to the right side of the system, on one side of this defect I'll have an odd path, and on the other side I'll have an even path, or the other way around. Okay? And now you can use this in order to direct the region where stress would concentrate. So what you're seeing here is a demonstration of, again, it's the exact same system, but pressed with different textures on its left-hand side boundaries. In this case, we designed things such that all the energy or stress would concentrate on the top side of the defect, and here we designed it such that all the defect would, the energy would concentrate on the bottom side of the defect. Again, it's the same system, the same mechanical metamaterial, but just with slightly different or opposite phase of the boundary load that we're putting on it. We can similarly build a system with two defects, and then the path going through it would either have an odd length and then stress would concentrate there, or it would have an even length and then you would not have any stress there, and stress would be in the regions outside this gap. And now we can generalize this to 3D. So in 3D, the basic object, which is either defected or not, is an edge in the lattice, and it turns out, or we showed, that these defect lines cannot terminate or branch in the bulk. So in every vertex in the lattice, you need to have an even number of defected edges meeting there. So you could have some crosses, but you cannot have a point defect. So this defect, one possibility is that these defects end at the boundary. So you have a defect line here running through the entire system, and then when you press from these two sides, stress is concentrated, say, on one side of this defect. In 3D, you have a bit more richness, so you can, for instance, twist this stressed region, as we're trying to show here. It's a bit harder to see things in 3D, as you probably know. In 3D, you can also close a loop, a closed loop of this defect line. So this green line here are the defects in the lattice, so they form a closed loop. And again, this is the exact same mechanical system that we're putting on it two different loads that differ just by the phase or a global flip of the texture, and and in that way we can cause the stress to concentrate either in the region going through this loop of defects, or to avoid that region, as you're seeing here on the right. Okay. So far, I considered blocks that have just a single floppy mode. Now you can similarly try to so therefore the entire structure would have either 0 or 1 floppy modes. Now if you remove a bond or remove a constraint from your building block, each block would now have 2 floppy modes. So now when you build a lattice in which you combine also these blocks that we call T1, you can have many floppy modes, and we've shown that you can have more or less any number of floppy modes, between not having any floppy modes at all, namely having a rigid system with frustration in it, as I showed before, to having a system in which the number of floppy modes grows extensively, grows linearly with system size. And we can also design the shape of these floppy modes similar to what I showed with a single floppy mode, that we could design its shape, right? We could make our material smile, so we can now have multiple such modes and design each one of them separately. And hopefully I'll manage to show you a small animation, follow the story. So these are our T1 blocks that have 2 floppy modes, and this is our T2 that has 1 floppy mode. And again, using the same concept of a spin model with antiferromagnetic interactions, whenever you have a connection, you can build a lattice that has multiple floppy modes that you can actuate each one of them independently. So here I have a loop with an even perimeter, therefore it's floppy, and it's disconnected from the rest of the lattice. So each time we excite a different mode, the other modes are not excited to linear order. The deformations here are small enough such that the higher order effects are negligible. And here, this last red loop you're seeing here has an odd perimeter, and therefore it's rigid, and it's much harder to deform. Okay? So the little bit of deformation you saw there is just imperfection at the hinges in this Lego system. But the issue when you have multiple such floppy modes is that these different chains cannot cross each other, because if you have two chains crossing, the point of their crossing is common to both of these chains. So if you'll excite, say, this pink mode here, you'll move the yellow dot here, this vertex in the lattice, and that would excite also this blue mode here. So if you want to have several modes that cross each other, if you want to simultaneously have different modes in the system that you can excite each one of them independently, you can want them to cross each other, you can do that by going to the third dimension, as I'll try to demonstrate here. So this is a demonstration of, and again, if you can switch down the sound. So here we have two loops, one the red one that we've just excited, and the yellow one that's being excited now. And you can see that these two loops are essentially linked one to the other, such that they are topologically connected, but there's no contact between them, and you can excite each one of them independently, as you just saw in this video. Now we can, speaking of applications, we can use this in order to design sequential actuation. So this is now a 3D printed metamaterial using this concept, which has three chains shown here in the left, and all the rest is rigid. And as you probably saw, these three chains were excited simultaneously. Whereas if we use a material that has plasticity in it, there's a nonlinear effect such that first the shortest chain is excited. Only when it reaches its maximal amplitude, the next one is excited, and the next one. This is a structure in which all these three chains have the same length, and there's some spontaneous symmetry breaking that one of them, by chance, is the first to be excited. Once it's excited, this nonlinear effect causes it to continue until it reaches its maximum amplitude before the next modes are excited, as hopefully you managed to see here. So just one last thing. I think I have a minute or two. So I told you mostly about combinatorial metamaterials, in which we have these structures that are not necessarily periodic, and we use these orientations of the block in order to control frustration in the lattice. Using this analogy to artificial spin ice, we also came up with a periodic lattice that has a frustration in it, and we use this in order to demonstrate that this, if you want, glass-like system that has an extensive set of metastable states, how its dynamics are also, non-trivial if we want. And one demonstration that we're showing here is how the response of the system depends on the sequence of operations. And hopefully you managed to see this video. Maybe not. Could you try clicking on the video? I don't have access to the presentation. Let's try again. Okay. Do you can you just click on the somewhere in the video? Okay. Anyway, I'll try to explain in words. So we showed here some demonstrations of using this mechanical system that has multiple stable configurations. We analyzed the graph of transitions between the different states of the system, and these transitions occur due to external manipulations that we apply in the system, and we use that in order to demonstrate how, even if we perform the same operations of the system, the sequence of operations determines the final state, and therefore we can use that in order to infer information about the past of the system. Namely, if we measure the final state, we could identify what was the sequence of the operations that were performed on it. And there's a nice video. It's out on YouTube. You can search for it and see it on your own. But anyway, that's another small piece, and I think I'll sum up just by, very briefly showing you all the different things I tried to tell you about, related mainly to combinatorial metamaterials, and I'll just leave here this, final slide saying that, at least my take of why it's worth looking into into metamaterials generally is that these systems often naturally have discrete behaviors, and it's very natural to define in them, to describe them using spin models. And then there are interesting things in condensed matter or statistical physics. Sometimes these things map to a problem that someone solved before you were born. Sometimes they map to a problem that no one ever considered before. In both cases, it's fun and interesting. Specific, effects or features that I've encountered so far is all this notion of frustration, defects, and topology that I touched upon a bit. And once you have a good understanding of these systems, you can make them respond in unusual and desired ways, and maybe down the road this will also lead to applications. I'm saying maybe, again, I know there are people that are stronger in taking things to applications, and people are working and doing all kinds of cool things with metamaterials today. I'm not that strong in that, and certainly Cambridge has really nice roads that you can go down them and reach interesting places. Thank you.
Thank you for a very nice talk. So we started a bit late, so we have time for a few questions.
Can we use the mic?
Really interesting, thanks. You sort of made a point to contrast the kind of holographic metamaterials with the non-holographic one. Is there something kind of in between, or neither, where the scaling is not as the surface area or the volume, but has some sort of a, fractal structure to it?
Wow. So again, holographic order, I think it's something binary. Like, okay, either you have that symmetry or not. About whether how things scale with system size. So actually, so far, all of the building blocks that induce holographic order have a sub-extensive scaling of the number of possible metamaterials you can build with system size, whereas those that do not induce holographic order have extensive scaling. So that's just an empirical result we have so far. We don't have a proof that that's generally true, but we already have sub-extensive scaling. So but nothing fractal yet. I don't see. I didn't identify yet the way to get something that would be fractal.
Thank you very much for a very nice talk. I have a question about the condition you found to have, the compatibility condition to have these modes on an extended scale, mapping onto, for example, spin-ice or other frustrated systems. When you have rules like the spin-ice or dimer rules, you tend to have emergent gauge symmetries that are characterized by power law correlations among the, in your case, displacements or in the spins, etc. And you can have various types of gauge theories. The spin-ice and dimers are typically U1 and power law correlated. You could have Z2 and short range. Have you considered whether this has an effect on the modes, on the mechanical properties, or if it's not relevant in this case?
No, so once you have a floppy mode in the system, I don't know how important it is, whether you have, what is the spatial dependence of the correlations, but certainly for the design process, and maybe I'll just say a word about that. So there are two different problems here that should be analyzed. One is what we call the ensemble of possible configurations or design space, and then you can consider all the possible configurations you can have. But a separate question is, once you decide on a certain configuration, and I know you send to the 3D printer and you fabricate your material, or I know you build it by hand, now there's a second issue, which is the deformation field of that given structure. So for the second thing, once you have a given structure, whether there's a mechanical difference, if your floppy mode has a certain correlation or other correlation, we didn't identify anything, and I don't think there's a lot there. But for the other issue of design space and all the possible structures you can have, and relating also to Anton's question about the multiplicity or degeneracy of these things, then certainly different building blocks that map to different spin models could have different symmetries and therefore different correlations. And yes, we have, for instance, once we map to the ground state of these frustrated Aviv models, that they have algebraic correlations. So these things appear there, but we did not identify mechanical consequences. Yes.
We have time for maybe one quick last question.
So, if I understand correctly, these floppy modes have vanishing energetic barrier. So, if you apply a finite load beyond this finite threshold, don't you immediately go into the rigid regime? And is everything homogeneous and isotropic and boring there?
Yes, I think that for very high loads, it would indeed be boring. And I'm showing you only the interesting regime,
okay.
Obviously.
I mean, nothing of the inhomogeneity of the floppy case go into the rigid case.
Okay, I don't know. I think that indeed things would be boring once you go to very large deformations. But the thing is that, again, I'll just reiterate this notion of designability, that if you have a certain application in mind, you can make sure that the range of deformations that the soles of your shoes or the wing of your airplane or whatever are going to have, you can design your structure such that the relevant deformations that this material or engineered system would eventually undergo would be in the interesting regime where you want to take advantage of